Okay, hello everybody. It is my great pleasure to welcome Bhishan Jacelon. I mean, he was around for quite a long time, but now it's his turn to give a lecture, and his application of classification of sister algebras. We're very happy to have you. The presume is yours. The floor is yours.
Thanks. So first, let me say that I wrote up some notes for this mini course I'll be giving, and I put them on my website, so you can find them here. All right, just some 100 notes. Let me start straight away. So before I even get to the plan or the overview for this mini course, I want to straight away say what I mean by classification and give you some examples of sister algebras to bear in mind that are applicable to this classification program. So introduce what I will call a classifiable category. I'll denote it by E for Elliot. So the objects in this are unital. I see. Okay, need to be careful there. Unital, infinite dimensional. Simple, separable, sister algebras with some couple extra hypotheses. So the first one is finite neutral dimension. Well, okay, let me say the first one is the universal coefficient term. So the UCD and with finite neutral dimension. I will, in due course, describe these assumptions in some detail, some more briefly than others. So these are the objects in the category, and the morphisms, or just unital style morphisms. Okay. Then often
oh, wait, so I assume more than nuclearity, you assume actually finite nuclear dimension.
Yeah. That is a thing. As pointed out, a strengthening of nuclearity, and I'll get to this actually today, and I will motivate the definition from nuclearity. Okay, so sometimes, I mean, it's a bit of a joke, but just to abbreviate all of these hypotheses, we call objects to be classifiable sister algebras. So classifiable sister algebras are the ones that are classified. So objects in E are sometimes called classifiable sister algebras.
This infinite dimensional is related to being purely infinite.
No, I just mean infinite dimensional as a vector space.
Yes.
The vector space.
Yeah, but it's crucial for me to include this for reasons that I will get to also today. All right, and the reason I put unital in parentheses here is that a lot of what I'm going to say throughout this mini course apply also in the non-unital setting. Things are quite a bit more complicated there, and I don't want to get into that. Oh, so just the simplicity all the time is, well, you know, the vast majority of the time being assuming that things are unital. Let me just say that I won't really say anymore is that in the non-unital setting, you often demand some extra conditions. So one often, let's say, restricts to not just simple, but algebraically simple sister algebras. And also often you demand that the simplex of tracial states is compact.
Please forgive me by my ignorance, but what do you mean by algebraically simple? How does that differ from simple?
So simple means no non-trivial closed sided ideals.
So close, okay.
So it's a fact that every unit of simple sister algebra is automatically algebraically simple. This is a fact. But not so in non-neutral case. So this is something we can demand, and we want the compact.
Take compact operators, so it's simple as a sister algebra, but have lots of interesting ideas, trace class, whatever.
Sure, indeed. And when I say trace space, and again, I will go through this in some detail, I mean the space of tracial states. So again, both of these are automatic in the unital case, not so in the non-unital case. And then as far as morphisms go, you might want to restrict to some kind of at least tracially non-degenerate morphisms. Okay, but as I say, I don't really want to get into that. So that's what the setting is, for classification, and the Elliott invariant.
Space is what? Space of traces?
Tracial state.
Space of tracial states.
Okay.
Yeah, space of trace, yes.
Normalized.
Normalized, yes.
Yes. But I will go into this in some
Yeah.
detail in due course, maybe next time. Exactly what I mean by trace space and what kind of structure it has. Right, so the Elliott invariant is this functor, so L A, the sister algebra A.
Sorry, what do you mean by a state for a non-unit sister algebra?
Norm one. So a positive
norm.
A positive linear function that has norm one. So the Elliott invariant is this fixable, so it's the K0 group. And again, I will today, maybe start with it, depending on how things go, and certainly next time I will go through K theory in some detail. The K0 group, the distinguished cone of a positive element in the K0 group, the class of the unit in the K0 group, the K1 group, this space of tracial states, and a pairing map between K0 and affine functionals on the trace space. All right, so roughly, this part is telling you something about projections in the algebra. Well, in matrices over the algebra. This is telling you about unitaries. These are the traces. And this is the pairing up, as I said. And by pairing up, I just mean the evaluation up. So rho A of the class of a projection applied to a trace, it's just the evaluation of the trace of that projection.
A fine of place involved.
Again, I will go through this in some detail, but what it means is that, so this trace space, it's a compact convex set. So I just mean the continuous maps from that set to the real numbers that preserve convex combinations. So, right. Yeah, okay. One thing I want to mention is that these days, one often kind of subsumes this positive cone into the rest of the invariant. So this, the order structure can be recovered from this pairing. pairing is what's called weakly unperforated. Assuming. And this weak unperforation, which maybe I will mention at some point, is automatic for the classified C-star algebras. Okay, so that's what the C-star algebras are, these infinite dimensional unital classical finite dimension UCT. This is the invariant. By the way, so this is, I said this is a functor. I'm at no point going to try to make precise what the target category is. It's a little bit complicated because we have these various components with lots of different kinds of structures. So this is an ordered abelian group. It's an abelian group. This is what's called a Choquet simplex. This is a group homomorphism, and even worse, this is covariant. This is contravariant. But this doesn't matter. It's not at all important for what I'm going to talk about.
Would you be able to get a date? When did George come up with this invariant?
So this invariant was gradually built up over the years. I mean, this part, the K0 group, the order structure, the class of the unit, is already present in the classification of AF algebras, which was when 79-ish, 80, something like this. And then with more and more examples, some of which I will mention, it became clear that you needed more. You needed to add more and more and more to the invariant to classify. So,
and this pairing, when did it come to the picture?
So this pairing proved necessary, I think, in work of Goodall, and this was probably in the early 90s. So Goodall constructs these algebras that cannot be distinguished from, I don't know, maybe UHF algebras, don't quote me on that, except unless you consider this pairing. So I think by the early 90s, also, all of this was clear that all of this was needed.
Because it smells cyclic homologies, I want it to be.
I see. I could not comment on that, unfortunately.
I have to make sure that it was after the advent of cyclic homology.
I see.
And yes, it is.
Got it. Got it.
I don't know much about these things, but was it something like punctured the K theorem what
Punctured K theory? I'm not sure I know what this is.
I've never heard of it.
maybe I found this or something.
Maybe Tomek, you know?
No.
Yeah, I'm not sure.
Okay, so I may be mistaken.
Okay.
Also, the invariant can be calculated to any C-star algebra, not when the classifier.
Yeah, that's right. Yes, yeah, absolutely. But this makes sense for any C-star algebra.
And a classifier with this, let's say, a pool invariant.
Yes, this is how I understand.
Yeah,
exactly.
Exactly. I mean, the remarkable thing is that yes, for these classifiable C-star algebras, this is enough. Okay, so with that in mind, let me.
The traceless state set is space is empty,
Yes,
but
yes. I will address this. Let me state the classification there. And this is due to many people. I'll just write a few names. So indeed, in the case when the trace space is empty, this is what's called the Kirchberg-Phillips theorem. And there, in this case, the invariant just reduces to K0 and K1 on the class of the unit in K0. So it becomes much simpler in this case. So this is TL infinite, and I'll explain in detail what this means eventually. And then, okay, so when Jack was giving his lectures last month, he mentioned the crucial puzzle piece, this capricious White-Winter theorem. Let me mention just some other names. So Elliot, but I'm really not going to try to be exhaustive, just to give you. So Gong, Lin, New. Okay, blah. All right, so this and the dot, this is the stably finite. So for now, just think, as Manish was asking about, this is the case where you have empty trace space, and this is the case where you have non-empty trace space. And maybe I should also mention, so see also this recent paper on the archive by Jose Carrion, and his co-authors. So Jamie Gabe, Schaffhauser, and Gracious, Stuart White. Hope I didn't forget anybody. All right, so the theorem is that if we have two objects in our category, then they are isomorphic if and only if the LA invariants are isomorphic. And it's a functorial classification, meaning that I've written it the other way around, but okay, if you have an isomorphism at the level of the LA invariant, then you can lift it to an isomorphism of the algebras. So that is
The question.
yeah.
Can we replace this specific trace by functionals on these traces?
Yeah, absolutely. Yes. Yeah, absolutely. And in practice, that's how it works. In practice, often you are working with affine functionals on traces. It's just dually equivalent. Yeah, sure.
So then it's much better because this is a covariant factor.
Good point. Good point. Yeah, that's actually a very good point. Okay, so this is the classification of objects in the category. Later on, we'll also talk about classification of morphisms. So later, classification of morphisms. So what I mean, just to get into what I mean, first of all, note that if I have, let's say, two unital star homomorphisms between two objects in the category, or just two C-star algebras, let's say two unital C-star algebras. We say that they're approximately unitarily equivalent, and I'll write it equivalent AU. So phi is approximately unitarily equivalent to psi. If there's a sequence of unitaries that phi is the limit of UN by a UN star. So for all A and A. All right, so that's what approximate unitary equivalence means. It's relevant to this because the LA invariant cannot distinguish morphisms that are approximately unitary equivalent. So if they are AU equivalent, then they induce the same map at the level of the LA invariant. So if phi is approximately unitary equivalent to psi, then L phi is L.
I'm a bit confused. If unitaries are where? In the C-star algebra?
NP, yeah, NP. Okay, if you're non-unital, you might want to take them in utilization, but let's not worry about it. Okay, so
Sorry, is it important that all UNs are unitaries?
yes. I mean, okay, depending on
Enough to have some UN which are partial isometries and eventually they become unitaries.
sure, yeah, sure. I mean, you only care about yeah, and you only care about what happens asymptotically. So yes.
Okay.
And this depending on the context you're working in, this can be weakened. You only need them to be sort of approximately unitary. They act like a unitary on a sufficiently large set.
Yes.
Yeah, sure. Okay, but the point I want to make now is that the converse is not true. So the LA invariant is not enough to classify morphisms up to AU equivalence. So the converse is not true. So in general, I mean, sometimes in certain circumstances it does work, but in general, you need a finer invariance than L. And I will discuss this in some detail, maybe, I don't know, either Friday or the next week. I'm very variant.
Of course, if P needs non-inner automorphisms, it's obvious.
Sure.
But yeah, but in the case when all automorphisms are inner in B,
Even
still so.
one of the algebras I'll get to shortly is the Jiangsu algebra. Every automorphism is approximately inner. And it's still not enough. It's still not enough. Needed to classify. To a few equivalents. So you need to add some stuff, which I will describe. Okay, so that's what I mean by classification. So morphisms we'll get to later. For now, I mean classification of objects. Okay, so it within this nice, well-behaved class of C-star algebras, which is actually quite broad. I'll give some examples right now. If we know that the LID variant is the same, then we know that the algebras are isomorphic. So here are some examples to bear in mind. Well, maybe a class of examples. So these are simple, approximately subhomogeneous algebras. So ASH, approximately. Subhomogeneous. Algebras, what's called bounded dimension groups. Actually, slow dimension group is your orthograph. Let's just stick bounded. Let me explain what this means. So first of all, what does subhomogeneous mean? A C-star algebra is subhomogeneous if it is a subalgebra of homogeneous C-star algebra. So meaning it's a subalgebra of continuous functions. Let's say for this definition, it could potentially be non-uniform. So subalgebra of continuous functions on from some locally compact alpha space into some matrix algebra. Okay, so that's what subhomogeneous means. Equivalently, there is a bound on the dimension of irreducible representations. So this is equivalent to, I think we could lock it out. That there is some n such that every irreducible representation of A, as I mentioned, at most n.
I have a question.
Yeah.
Why people define AU equivalence only on the level of the counter domain?
You mean
Only twistings on the counter domain are allowed. What about doing the same in the domain of this morphism?
yeah, you could do that. Does this give you anything different? I mean, if the morphism is unital, then okay, I guess yes. So if it's equivalent in this sense, then it would also be equivalent with it in the codomain, but maybe is it genuinely a stronger notion? Yeah, I guess potentially it is. Yeah, I don't know. I don't have a good reason for why to not consider this kind of equivalence. I don't know.
Because this kind of AU equivalence means simply that you are classifying, in a sense, representations of a fixed A,
yeah,
in some B.
Yes. Mm-hmm. Okay. Maybe one kind of answer to your question is that in this classification of morphisms, the way it works, the theorem that holds by it's in, for example, this work of Carrion and Scorthus, is you can classify yes, you want the codomain to be in E, but the domain can be something quite more general. So domain doesn't have to be simple, for example. So you can classify morphisms from a commutative C-star algebra into something.
So it's about classification of arbitrary algebra.
Yeah.
In your given algebra of your class.
Yeah, that's the way it seems to work out. Yes.
Oh, good idea. Okay.
So that's what subhomogeneous means. And
Sorry, is a capital N and this lowercase k basically the same thing?
no, not necessarily. Not necessarily. It means this k could just be arbitrarily large. You could just take an amplification, I guess. I don't know, to be honest, how this is proved off the top of my head. So I don't know what, if you take like some optimal k in whatever sense, whether this, I guess, yeah, I mean, it's because, okay, what are the irreducible representations?
That's exactly what I'm looking at. It's bounded by k.
Yeah, so if you took this homogeneous algebra,
Yeah.
then yeah, the irreducible representations, just point evaluations.
Yeah.
Then this k would be this n.
That's all I wanted to understand.
In general, it might be a bit more subtle. Okay, so that's what subhomogeneous is.
So the dimension means k.
Sorry.
Dimension means k.
No, I just, okay. I mean, A is just a sub-algebra of this. So you could have irreducible representations which are not just point evaluations. And I'll give you an example shortly. We'll come to an example. So it's not the case necessarily that all of the irreducible representations have dimension k. You could have some with different dimensions.
Yes, then we could have blocks, for instance.
Exactly. Yes. That's the exact example I was going to give you. Yes. Okay, but this somehow is
It's about finiteness, really.
it's only about finance,
And I don't understand fully this relation between k and n.
Yeah,
I'm not claiming that there necessarily is an immediate relationship. I'm just saying that if there is some n, so that bounds the dimension of irreducible.
So there exists k,
There exists k, yes,
there exists n,
for some k.
or some k, okay?
And I'm saying that's the definition of subhomogeneous. I'm saying theorem, that is equivalent to there is some n that bounds. I'm not in this statement claiming any relationship between k and n, even though there might be.
the other way around, if we take this particular C-star algebra C naught x m k, that's, I guess, true, that the bound on a dimension of the reducible representations is k.
Yes.
Yeah, I suppose that's true. Yeah, good point. Yeah. Okay. All right. So that's what subhomogeneous means. Approximately subhomogeneous means we take an inductive limit of these things. So A is inductive limit of A n's by n's. This would be subhomogeneous. So, in other words, it lives in some C0 x, let's say m k n, let's say x n m k n. And I said, so that's what approximately subhomogeneous means. And I said of bounded dimensional growth, that just means that the dimension of these xn's is bounded. So we want, so bounded dimension growth means we want the supremum n of dimension xn to be less than infinity. So this is bounded dimension growth. All right, and then the dimension here, I mean Lebesgue covering dimension, which I will remind you what that means.
So speaking about this direct limit, you
Yeah.
must assume some embeddings between MKNs.
And yes. So
Unital, non-unital.
I'm at the moment saying everything is unital. So let's say these are unital.
Oh, so then there are very few embeddings between matrices.
Well, no, I mean, so these could just be, let's say, the complex numbers, and then we're talking about maps between compact Hausdorff spaces. Many maps between compact Hausdorff spaces.
Yeah, but between, okay, so I don't, so how are related these C0 xn to mkn for different n? Do they form a system?
Not necessarily, because all I'm saying is that the maps in are an to an plus 1. These are subalgebras of this.
Mhm.
They may or may not extend to the whole thing, may or may not.
Okay.
Okay, I mean, if we drop the
Algebras form a system.
if I could drop the S, this would be approximately homogeneous, and then effectively I just mean I'm not talking about subalgebra, I'm just talking about these. And then yes, we are talking these would form.
It could be unrelated.
Yeah, absolutely,
Okay.
potentially. But often it might be the case that we do have an extension to the bigger algebra. I'll give you some, in fact, I'll give you some examples of what kinds of star homomorphisms we typically get in that.
But this bigger algebra is potentially non-unitary if Xn is non-compact.
So let's
I mean, it's C0.
Yes.
let's forget.
Okay,
Everything is unital.
okay,
Let's not at all entertain this non-unital
okay.
possibilities. Everything's like,
So the diode limit could be not unital, of course.
Yes.
Still.
I don't know, I mean, these are unital.
No, this. If you consider that.
Yes, I see, right, yes, exactly, yes.
Okay, so please correct me if I'm wrong.
Yeah.
So these algebras are called sub-homogeneous.
Yeah.
And this, what is this?
Homogeneous.
Yeah. Okay.
Yeah, exactly. The name is a good one, I think.
Yeah.
So homogeneous means in terms of this Blackadder theorem that there is every irreducible representation is the same dimension. And it turns out to be equivalent to its of the form continuous functions by some matrix. Okay, so that's what I mean by approximately subhomogeneous. These xn's are just some compact Hausdorff spaces. Here's some examples of what the xn's could be. So I could take, for example, the xn's just to be a collection of points. Right, in other words, and then I'm just talking about continuous functions from points to matrices. So I'm talking about finite dimensional T-star algebra. So in this framework, I get AF algebras. So AF algebras, so in particular, UHF algebras, say, are examples of these approximately subhomogeneous algebras. And I'm claiming that these simple ASH algebras of bounded dimension growth fit into this category E. So AF and UHF algebras are in the category. If I took Xn to be collection of intervals, I get what are called AI algebras, approximate interval algebras. These are in the category as well.
That's not artificial intelligence.
It's not artificial intelligence. And if I took Xn to be some circles, then I get AT algebras. I don't know why I'm using S1, but T, whatever. So algebras. All right, so all of these, and I guess what I'm also saying here, I suppose, is these are homogeneous examples. Let me give you some truly sub-homogeneous examples, which are very important in this framework. So these are what are called dimensions of algebras. So these are examples where we do have a change in the dimension of irreducible representations.
So here xn's are like finite unions.
Yeah.
Only finite.
Yes, yeah, finite units, yeah, finite.
It's because he removed 0. C, not C0 anymore.
Yeah,
What requirements are there with?
No, like
Finance.
bounded dimension.
units of star homomorphisms.
That's it.
Yeah. But I'll show you in practice what they look like. Sure. Sorry, you were saying?
No, I was saying because of the bounded dimension growth assumption, I think you are taking finite union, right?
Well, I mean, the dimension of
No.
infinite collection of points is still 0.
Right, this is discussed.
Okay, so another example of what Xn could be are these dimension drop algebras. I'll denote them by Z Q. P and Q are some natural numbers. And these are, so it's a subalgebra of continuous functions from the interval into the matrix algebra MP tensor MQ or MPQ, in other words. And we introduce some boundary conditions at 0 and at 1. So we want them to be, as suggested earlier, block diagonal. So F0 is in the block MP tensor 1Q. And F1 should be in the block the other way around. So 1P tensor MQ. Wait, so what are the, just for the sake of the earlier discussion, what are the irreducible representations of this algebra? Inside the interval, so open 0, 1, it's just point evaluations. Okay, but at 0 and at 1, it's not just the point evaluation because I have a direct sum happening here, and a direct sum happening there, so they're not irreducible. So inside each block, I have an irreducible representation. So at 0, I have a p-dimensional irreducible representation, and 1, I have q-dimensional irreducible representation, right? But there's still a bound, so it's self-homogeneous, but not homogeneous. All right.
Do people use the notation that it's a join of NP?
Yeah, that's exactly what I was saying.
Like a product, you mean?
No, join.
Join.
Join of spaces,
Join of two algebra, dual.
like in Milnor function.
I see. Yeah, I don't know.
Dual version of the construction of. the
Yeah,
product.
because
I see.
topology, if you have X and Y, the join is X cross Y, cross the unit interval. And at 0, you collapse X to a point, at Y, you collapse, at 1, you collapse Y to. This is
Yeah.
the joint construct.
I see. I mean, I don't know how common it is to use the same notation, but I would not be surprised if that's where the inspiration for this comes from. All right, so let me just say that the Jiangsu algebra is the unique simple monotrivial monotrivial means there's a unique tracial state. So limit of prime dimension drop algebras. Prime ZPQs. Prime just means that we want the integer p and the integer q to be co-prime.
Does monotrivial mean that dimension of space of traces is 1?
Yeah, no, it is.
That's one.
There's just one.
That's one trace.
Yeah, there's one trace.
Just one trace.
Yeah.
Normal.
Yes. By trace, I all the time I say it. Yes.
So it's the same.
Sure. Yes. Yeah. That is the thing. It's back. Yeah. By the way, so a note about the structure of this. This is a universal C-star algebra. I mean, the constant one does satisfy these boundary conditions, but that's the only projection in the algebra. It's projections. So this Jiangsu algebra, it is unital and it is projectionless, has no non-trivial projections. So that's how it was constructed in Zhang Linsu's original paper as this inductive limit. It is also another sort of more abstract characterization. It's that it is the unique object in C in the category E. That has the same L invariant as the complex numbers.
Sorry, by this limit, you mean the direct limit?
Yes.
And monotration means that these maps in the system preserve this unique normalized trace.
Well, so there are many traces on each block.
Yes. So what is happening?
What's happening is that let me show you in a second, right after this, I will show you what the connecting maps typically look like, and then we can discuss what's happening at the previous one. It's okay. So the Jiangsu algebra is
Limit is monotration.
Yes. So what's happening is that the maps are collapsing traces. There are many traces here, but when I go to the next stage, I'm sort of collapsing the big tracial simplex to something smaller, like at 1.
But I see what Tomek means, a bit confusing the way you write it, because it looks like if we have this adjective simple monotration, we have dozens of different limits. And only when you demand it to be simple and monotracial, it becomes unique.
Yes,
Yeah,
sure. Okay, yes, it's
yeah, that's what confused us.
the unique limit of prime Z that is simple and is monotracial.
That is good, yes.
All right, by the way, so this is why, an example of why I need to include infinite dimension in the season, otherwise it's not true. Okay, so let's now discuss what the connecting maps, as they're called, typically look like. So, in practice. This map, so phi n, from one sub-homogeneous guy to another, looks like this. Okay, so phi n applied to some function in here. So it's mapping it. So let's think of this as living on x n plus 1 m a n plus 1 and this living in x n sorry n m a n. Let me
Okay, I see. Yeah, sorry about it, but I didn't touch anything for sure.
okay, well, okay, I guess it's a shame that it's got lost apparently, but as I said, I did put the notes on my website. I'll just, again, if you want to, the notes are here. All right. Okay, so I was saying that these connected maps, they look like this. So I'll just be careful how I do these dots, I guess. X dot. I
don't think it was related. No, but you never know.
Okay, so this is for this for x in x n plus 1 f in this an for some. Okay, let's think about where things should live. So x is in xn plus 1. These size, I want to get it to somewhere where I can apply f, so that, you know, contrariantly, they're going to xn. So for some continuous maps, psi I from x n plus 1 to xn. Okay, that's almost, but not quite true. Why should we expect this? So when I apply this morphism phi n, and then I evaluate at a point, what am I getting? I'm getting a map from an into some matrix algebra. So I'm getting a representation. We know that every finite dimensional representation is just going to be a direct sum of irreducible representations. But I should allow for some unitary, because the irreducible representations are up to unitary equivalents, just these point evaluations. So it's like this, except potentially with some unit. So typically, this is what the connecting maps sort of look like. Block diagonal modulo some conjugation by.
So F has values in M.
Yeah, so this,
N,
yeah, MKN, yeah,
MKN, yeah, yes,
Mhm.
okay.
so this should be,
You can add zeros below and
I could add zeros, except I want these to be unitable, so no.
Yeah, but zeros are off diagonals.
of the diagonal zeros.
Of that, yes, what do you mean add zeros?
Well,
I mean, everything else is zero.
To make it opposite.
I see. What you mean, I suggested that I should add zeros. Okay, I see. Yes. I thought you were saying that we could also have the zero. Okay. Yes.
So in the construction of Jiangsu algebras,
Yes.
you can explicitly say what the CIs are.
So in the Jiangsu construction, the maps, so from one stage to the next, there are one of three kinds. They are either constantly a half, or they are the map x plus 1 over 2. Oh, sorry, that's x over 2. X over 2, or they are x plus 1 over 2. Okay, and then, it's just how many of these you include, you do the number crunching just to make sure that the boundary conditions are satisfied. Okay, but these three maps do it for you. And what you should observe here is that these, the slope is a half. When I do a sequence of these maps, I do many times, what I'm going to get is that I'm going to get a spread of these linear functionals, except the gradient is going to be 2 to the k or something like this. So what's happening and what's making the limit monotracial is that these functions are becoming approximately constant. So in the limit, it looks like the trace is just evaluation at some point. So that's so if I start at some an and then I map very far along, then any trace in the new algebra am will be approximately the same as just evaluating at a point. So all the traces will approximately agree up to some epsilon on whatever finite set you started with.
So the construction depends apparently on psi i's and uns,
Yes,
but in the limit, no.
in the limits, these don't appear. Because we have classification, as long as we get the same invariant, we know we get the same thing. So there are many different ways you can do this, and this is not the only construction of the Jiangsu algebra. There are many different ways to do it, but this works. This gives you the right invariant, which is all that matters. Okay, so maybe I hope this gives you some idea of what I mean, what's happening in this trace collapse.
and this drawing, it's a picture of what?
These are the psi-s. Sorry, these are the psi1, psi m. I'm saying in the Jiangsu algebra construction, these eigenvalue maps, as they're called, are just one of these three kinds. Either the function f of x is x over 2, f of x is constantly a half, or f of x is x plus 1 over 2. So in this case, these n's are just the interval all the time. So these are maps from the interval to the interval. All right. Okay, and then as far as so that's how you get monotracial. As far as simplicity goes, typically when you by the way, I said in practice they look like this. In low dimensions, this is true somewhat generally. In low dimensions, you can always kind of diagonalize like this. I think by low dimensions, I mean dimension of the base space at most 2. Also want some vanishing second cohomology group. This is a non-trivial result by Thompson that you can always kind of do this diagonalization. Yes.
So let me get back to this. So all xn's are just unit intervals, right?
In the Jiangsu construction.
In the Jiangsu construction.
Yes.
And now we are saying that all these psi maps are, which are maps from an unit interval to the unit interval.
Yeah.
We're always as one of these three cases.
Yeah, from one step to the next. Yeah, okay. But then when you do a composition after many steps, what happens is just you get a bunch more of these, but with slope decreasing.
Yeah, but a single one is always one of the three.
Yep, that's right. Okay, so that's the monotracial thing. Simplicity, maybe I'll just say this in words, is you often check simplicity by showing delta density. What this means is that you show that for every x, you want these eigenvalue functions to be delta dense. in the space Xn. Maybe I'll write this down. So for simplicity, show that psi1x, psi mx is eventually delta dense in Xn for any x. Okay, what I mean by eventually is, I mean, once you do this, so this is one connecting map. If you do sequence of them, then these will just be, these eigenvalue functions will just compose. I'm saying that you want that list of composed eigenvalue functions to be eventually delta dense for any delta bigger than 0. What's going on here is, all right, let's say in Xm, we have some function that lives here. So this is f, it's 0 outside. So I'm saying, let's say x is the interval. This lives in some ideal, right? So the functions that are 0 outside of its support lives in some ideal. So what I want is that eventually it doesn't live in any ideal. So eventually the support is spread out across the whole interval. And that is accomplished by making these delta dense. So if they're delta dense, and eventually at least one of them at any point in the codomain is going to live inside the support of F. So it's going to be non-zero, the image. Okay, it's not so important for us to fully grasp the ins and outs of this, but that's the idea. You just want to make the support spread out over the space eventually. Okay, so these are just, so the kinds of examples you should maybe at the moment bear in mind for things in this classifiable category are these simple inductive limits of subhomogeneous algebras with bounded dimension growth. In fact, these are very good examples to bear in mind because every object in the category looks like this. This is not obvious, but it's a theorem. So due to George, I think back in the early 90s, maybe in a slightly different form in paper Conlon and New. And this is that simple ASH algebras of bounded dimension growth. In fact, I think dimension at most 3 is what they get away with. They exhaust all possible LA invariants. So exhaust the range of E. So that means by classification, every object in the class is isomorphic to something like this. So every A and E. This one. All right, but that this is only true after the fact. It's important to note that this classification that theorem that I stated didn't assume any inductive limit structure going into it. It just turns out after the fact that yes, they've got inductive limits. So classification theorem does not assume any inductive limit structure. Okay, I'm at no point going to tell you how the classification theorem is proved. If you look at the archive paper by Jose Carreon and his co-authors, again, nowhere in the proof either using inductive limit structure. All right, so some other important examples of objects in E which are not a priori of this inductive limit form. So other examples in E. Importantly, for example, these cross products, these two algebras. So C of X cross, let's say Z, where alpha is induced by a minimal homeomorphism of the space. And where, and crucially, where X is finite dimensional. Dimension of X is less than infinity, and alpha is induced by a minimal homeomorphism. Minimal, I mean that the orbit of every point is dense, or equivalently, there are no closed invariant subspaces, no non-trivial closed invariant subspaces.
But in particular, such cross-product algebra admits some inductive limit structure.
Yeah, yes.
Is there some canonical way to produce this limit structure in that case?
Yes.
From the dynamics, I mean.
Yeah, yeah. You produce what are called these large subalgebras. So you, I don't really want to, but absolutely, yeah, there is some way of looking at the orbits of points and then creating some building blocks that are what are called not just approximately subhomogeneous, but even stronger, recursively subhomogeneous. And yes, you can build this.
So these matrices come from cardinalities of this finite sense orbits?
Yeah, it's a good question. I'm not sure off the top of my head. Yeah, but yes, it is true. By the way, so just a couple of comments on this. In fact, it's true that whenever I have a finite dimensional space and any homomorphism at all, then the cross product has finite nuclear dimension. I don't need any assumptions like minimality or anything. That's proved by Ilan Hirschberg and Jean-Charles Wu some years ago. So for proving finite nuclear dimension, I can get rid of minimal. I mean, minimal I need for simplicity, for example.
Then solve it.
Yeah, but one thing I cannot get rid of is finite dimensionality of things.
Here in covering.
I mean, Lebesgue covering dimension, which I will introduce shortly. Because, I mean, it's known that these constructions by Gilles and Kerr of some dynamics on infinite dimensional spaces, the Hilbert cube or something, where you do not have finite nuclear dimension as the cross product. So I can't get rid of this.
I don't understand this note. The classification theorem does not assume an inductive limit structure.
Yeah, so I'm saying here in this theorem that every object in E happens to be an inductive limit. Because they exist the possible invariants.
Yeah.
But I'm saying we don't need this fact to prove the theorem or to state the theorem.
Yes.
All right.
And which year was it?
Theorem? So I mean, so when George proved this, so George gives some explicit constructions of how to get any Elliott invariants in the early 90s.
Early 90s, okay.
Early to mid 90s.
Yeah, thank
I mean, Gongwin and you kind of reproved the results to get something a bit stronger. I don't know, within the last 8 years or something.
Okay, yeah, thank you.
So at first it appears that this ASH algebra should admit some traceable states, like because each admits.
Yes.
But you're saying that even infinite CST algebras are like that. So
Yes. So it's an excellent point. This is an excellent point. Very good point. Let me say that I don't want to address this issue. So exhaust the range of stably finite. Objects in very good point. So here, stably finite. I mean, there are to get the purely infinite case, you can also do a kind of inductive limit thing. This is showed my Michael rhythm, but you have to take, like, you basically take an inductive limit of circular algebras, then you take some endomorphism, some trace scaling endomorphism of that. Then you take the cross product, and that's how you get the purely infinite models. But yeah, very, very good point. Okay. All right. So, right. Let's just pause and think where we are. So I told you what the classification theorem is, and I told you what the invariant is, and I gave you some examples to bear in mind of algebras to which this theorem applies. Okay. So now let me tell you the plan for this mini course. It is what I intend to talk about. So first, I want to discuss some of the hypotheses in the theorem. So I want to talk about finite interdimension. And relatedly, set stability. I'm just going to be rather brief about this, but I'll at least tell you what these mean, what these words mean. Then I guess probably next time I will introduce K-theory. And I'll talk about the structure of what I've been calling trace space. And I'll talk a little bit about the Kuhn semigroup, probably on Friday. Very, very briefly, I'll mention at least a lightning quick sketch of the classification of AF algebras. And very briefly, I'll talk about T a little bit. Okay, so roughly, I mean, this is my plan for this week. Maybe it's a bit ambitious, we'll see. This is just going to be providing some background. You will hopefully, at least by this point, understand what the classification there is saying, what hypotheses are, what the components of the Elliott invariant are. And then I want to get in the next week or in 3 weeks' time, or whatever it is, then I want to get to the applications. I mean, okay, right. This classification theorem is tremendous. And as I said, I'm not at any point going to tell you how it's proved. What I am going to tell you is how useful it is. It really is a very powerful analytical tool, and that's what I want to get to in these applications. I want to tell you hopefully about 3 applications. So the first is what I will call the Weil problem. By the Weil problem, I mean, if you give me 2 normal elements in a classifiable C-star algebra, the problem is, can we compute the distance between the unitary orbits spectrally? This is a spectral computation. Of the distance between the unitary orbits of A and B. So for certain, I'm not going to answer this in full generalities, for certain normal elements in certain classifiable C-star algebras. All right, what do I mean by spectral computation? So why am I calling this the Weil problem? This goes back to theorem of Weil in over 100 years ago, 1912 or something. And the theorem matrices is that if you give me 2 self-adjoint matrices, then the distance between their unitary orbits is just the distance between the eigenvalues. So that's what I mean by spectral computation. So we first of all need to make sense of this in the more abstract setting of classifiable C-star algebras, and then solve the problem for at least for certain normal elements. Okay, so that's the first application I'll talk about. The second is I want to tell you about generic properties of automorphisms.
saving.
Again, saving objects. Right, so, okay, if you give me, let's say a stable Bhishan classifiable C-star algebra, so something that has traces, and the question then is, give me any old automatism, what does it look like? And what I mean by look like is at the level of traces. That's why I want to address this in stable Bhishan setting. So I'll tell you about mixing and chaos, so mixing and chaotic tracial dynamics. So what I mean is every automorphism of one of these classifiable C-star algebras that has traces induces a map at the level of the traces. And I'm going to show that generally it's very, very complicated what it does at the level of traces. It's chaotic and mixing.
Is mixing plus chaotic related to
Ergodicity. Yes, ergodicity. Yes, absolutely. Mixing is a strengthening of ergodicity. Yeah, I mean, by mixing, I mean weakly mixing. So it goes ergodicity, then weak mixing, then strong mixing. I'll talk mostly about weak. Yeah. But yeah, absolutely is related. Okay, so that's the second application, and then third application is my new favorite thing, something probabilistic. So C, I'll tell you about some probabilistic constructions. So I'll try to make sense of the question and then try to answer it. What is the probability that a C-star algebra is isomorphic to the Jiangsu algebra, given that it is in the classifiable category and it is KK equivalent to the complex numbers? Okay, yeah, it'll take some time to understand what this means and how to get the right structure to make sense of it. But for now, let me just say that, okay, I said the Jiangsu algebra has the same invariant as the complex numbers. It's KK equivalent to the complex numbers. What in particular, it also has a unique trace. So the variable here is that A might have many, many traces. So I'm saying if I take something that has the same K theory as the complex numbers, but potentially complicated trace space, what's the probability that in fact it has a unique trace? Essentially, is what I'm saying.
Conditional probability, right?
Yes, that's what I mean. Condition.
Is the question about some distribution on the space of traces?
Yeah, exactly. Yeah. I will show you how to construct random simplices.
Mm-hmm.
Okay, so that's the plan. Right, so let's start going through the objectives. So the first one was finite nuclear dimension. Let me tell you what finite nuclear dimension is, what the nuclear dimension is. And then let me motivate this by proving something that I guess we all know well, namely that every commutative C-star algebra is nuclear. Let's assume that,
But it might have infinite nuclear dimension, right? Because
absolutely. Right, so let's prove this. Let's assume, first of all, that the algebra is unital. And it's not really much more difficult to do in non-unital case, but let's just do this for simplicity. So assume, in other words, that A is continuous constants in some compact calculus. All right, so nuclearity, we could define it as unique C-star tensor products on C of X tends to B for NP. But I'm going to show that we have the completely positive approximation property. Let's fix, which is equivalent. So let's pick a finite set and let's fix an epsilon. So let's F finite and epsilon b bigger than 0. Right, so what do we need to do? We need to show that the identity map from C of x to C of x can be approximated by some completely positive maps down into some finite dimensional C0 algebra and then back up into the algebra. Let us, if all, let's take.
There is a request from Zoom.
Yeah.
Please define reality.
Yes, I will define it in the course of the proof. So as I said, I'm going to verify the completely positive approximation property. So the definition will come once I've proved. I know this is not sort of didactically ideal, but I hope you'll see where I'm going with this. Okay, so let UN be a finite open cover X such that every element of my finite set varies very little over each element of the couple. So such that for every I every F in F and X, Y in UI, we have F of X minus F of Y is less than epsilon.
What is capital F?
It's okay, yeah, it's fine. We fixed at the beginning. So
Okay.
yeah, we're fixing a finite subset of C of X, we're fixing an epsilon. Oops. So I fix this open cover. Next thing I do is let me fix a partition of unity subordinate to this open cover. So let's one row n the partition of unity coordinate U. All right, what I mean by this is that the support of each row I lives in UI. So each row I is non-zero only inside UI. And pointwise, these functions add up to 1.
Use are open, so support can be equal to you.
I think
I mean, open support contained, yeah.
it's contained.
Clearly contained.
It's equal.
But by support, I mean open support. Yeah. But okay, so it could be. So this is 1 for all X. Next. And let me also fix some points.
Sorry, so you don't assume that these supports are closed and they are entirely contained in UIs?
No, I mean, I
Some boundary points of the support of phi I
yes,
on the boundary of UI, for instance.
there could be, and I don't think that's important for what I'm going to say. We'll see if I have to take my words back, but I don't think it's important.
So this is some new definition of partition of unity subordinate.
Exactly.
I see. Oh, maybe I'm being sloppy. I mean, that's I see. Okay, so I should be a bit more careful. So I want the closure of these to be. Let's see. Okay. Let me say.
But by support one open is by definition the closed.
That's.
Well, okay, if you close a closed set, it's just.
I don't know. I heard some other people, maybe I won't name names, but I've heard some other people express strong opinions that it should be the open by definition, but whatever. Okay, let's say I mean this, that the closure.
So then it cannot be equal to UI.
But it's,
I guess not, if I'm saying this, but it could be, X could be zero dimensional, for example.
It's getting smaller.
All right, so if we're objecting to this, it's what, I see, okay, sure. I mean, but
yeah, but it's alternative, so it's okay.
Depends. Okay, if X is non-connected,
You're messing up. I mean, it's,
there exist subsets which are even compact and open.
it can be open and closed at the same time. I mean, you think of some disconnected pieces.
Yeah, connected component.
Yes. It's, you wrote everything correctly. Please put back this.
all right. Now, no one is happy. Okay, all right. And then let me fix, and fix points xi in U1. Okay, so to show the completely positive approximation property, as I said, we need to show that the identity map approximately factorizes. So I need to find some high dimensional C star, which in fact will be Cn in this case.
Yes.
And going back up, let's say, let's call it phi. So I want this to commute up to epsilon on the finite set F. Hope you know what I mean by F. All right, so I need to
Just please remind us which maps are what. So phi is very linear, one is ultra homomorphic, right?
for now,
Completely positive.
just completely positive for the moment. They're just going to be completely positive. Yeah. In fact, there will be much more, but
That's about it. That's what you require.
in fact, let's do it this way. So let's, just so I'm clear about what I mean by the definition of reality, let's say I want to do it into some matrix algebra MK, and I want phi psi to be completely positive. Okay, so this is what I mean by the completely positive approximation property. All right, you may complain that, okay, I should have in fact completely positive contractive, but I think it is true, maybe not very immediate, but it's true that if I have the completely positive approximation property, these are just CP maps, then I can deduce from this that I can get CPC maps. Okay, but anyway, by the CPAP, I mean that I have such a diagram for any F and epsilon. Okay, so now I need to define so these maps. So let's define phi. So this is just going to be C to the n, as it turns out. So CX to C to the n. And it's just going to be evaluations of these points. So phi F is F evaluated at x1, F evaluated at xn. Okay, so all right, this is not a completely positive map, it's star homomorphism in this case. But in general, we can't expect this. Just in the commutative case, we can, and this is what will work. Okay, so it's just these collection of point evaluations, and then I'm going to define the map going back up in terms of these partitions of unity. So I'm going to define psi, and this will not be a star homomorphism, so psi from C to n to C of x. So F maps to sum I from 1 to n. Oh, not F, sorry. I mean, an n-tuple of complex numbers. Sum lambda I rho I. Okay, so I claim that these maps, they have they satisfy the commutative diagram of the epsilon on the finite set F. So let's see. So let's evaluate the norm of so I need to do phi, first phi, then psi. So phi composed with, no, other way around, psi. Okay, let's let that be enough. And I have psi composed with phi of f minus f. I need to show that this is left and epsilon. All right, so what is this by definition? This is the supremum for x and x. This is the point valuations and this is the linear combination. So it's going to be sum I equals 1 to n. F I x rho I x minus f of x. All right, but in fact, these rho I think add up 1, so I can write this, I can stick in I equals 1 to n rho I x n.
And that should be f of xi in the first solution. Xj or something.
Sorry, yes, I wrote fi of x, it should be f of xi. Thank you. F of xi. Thanks. Okay, so this is at most supremum
I is equal to j.
yes, I is equal to j. I apologize. Yes, I need to be careful with i's and j's and x's. So and but okay, so let's use the triangle inequality. Let's take this aside. This is sum I equals 1 to n f of xi minus f of x times rho I of x. All right. Either x is not in the support of this rho I, in which case this is just 0, or is in the support of rho I, in which case this is by choice less than epsilon. Correct. In ui, f varies by step 1. So this is less than epsilon because these add up to 1. So this is less than epsilon. So that's it. Okay, so that was the proof that C of x is nuclear. We had this completely positive approximation property. But in fact, if we assume that the space X is finite dimensional in terms of Lebesgue covering dimension, then we can say more than this. And this will get us to the definition of nuclear dimension. So if the dimension of X is, let's say, n up for n less than infinity, we can say more. So let me remind you what I mean by Lebesgue covering dimension.
The covering dimension.
Yep. So the Lebesgue covering dimension of let's say a compact. So let's say X is compact metrizable. Let's say. I mean, there are sort of various ways of describing this dimension, and they're all equivalent in the metrizable setting.
So let me, Yang, are you trying to ask a question? Because I see that you are moving your mouth and you are not muted, but with that.
Oh,
now.
okay. Yes, I still. Okay, so basically, this nuclearity is just an argument from partition of unity. That's
yes. So in fact, in this book by Nate Brown and Taco Zhao, it's about nuclear inexactly throughout this great book. They say that partitions of unity were invented specifically to prove this proposition, despite what topologists might say.
okay, but I still do not understand this nuclear property in this context. I mean,
so nuclearity means exactly this: that a C surrounded by A is nuclear if the identity map from A to A can be approximately factorized like this. So if you give me any finite set F and any tolerance epsilon bigger than 0, I can find a completely positive map down into some finite dimensional algebra, and then another one going back up that makes this diagram approximately commute. It turns out that this is equivalent to uniqueness of a C star tensor product on A tensor B for any B, but that's very not obvious.
Yeah.
okay. Okay.
So it's some kind of weak notion of approximability by finite dimensional theta algebras. So it's very much not saying the algebra is approximately finite dimensional, meaning a limit of finite dimensional things, but it's some kind of weak. I don't mean weak in this technical weak topology sense. I just mean it's a weak notion of being approximated by finite dimensional things. So in fact, maybe I should point out there's some very recent papers on the archive by Kristen Courtney and Wilhelm Winter, where they're showing in quite a bit of generality that I can't remember off the top of my head, but maybe even something as crazy as any separable nuclear C0 algebra. Or maybe they need finite dimension, I don't know. But they can write it as an inductive limit of finite dimensional algebras, allowing the connecting maps not to be star homomorphisms, but what are called order zero maps, which I'll get to very soon. So in that sense, it really is quite like a finite dimensional approximation property if you allow for non-multiplicative connecting maps of these building blocks.
And from this definition, it follows easy that the tensor product is unique with any other algebra. The other direction is difficult, or both directions are?
I think both are non-trivial. Definitely one is more difficult than the other. And I suspect you're right. But yeah, neither is trivial.
And since we are at it, do you know why it's called, this property is called nuclearity? Why is it?
Yes, it's an excellent question. But
It goes back to Grothendieck.
does it?
So he is guilty, but he was a pacifist.
Yeah.
It's about integral equations represented by some integral kernels, and then representing these kernels as approximating these kernels by tensor products of one depending on, let's say, x,
I see.
another one depending on y, and in the limit you obtain the kernel depending on x and y.
Okay.
I remember it was Grothendieck who was messing up with these tensor products. So,
Yeah.
Yes.
But it's not just for C-star algebra, right? It could be for any like a topological algebra, right? It's this nuclearity. I think
there
probably
are
like
some
back in the
definitions
time.
of
Rosen didn't study this C-star algebra. I think probably he studied some like smooth functions, something like a Frechet algebras, I guess.
Yeah.
All right.
Okay.
Let me. Nucleus in Latin means kernel.
Nucleus.
Kern physics.
Is that right? Yeah, very good there. I didn't know this. Okay. All right. So the big covering dimension of a compact and tricycle space is at most n. If every let's say finite open cover W of X admits finite refinement let's say V such that at most n plus 1 elements of V can intersect non-trivially. N plus 4. No, I mean n plus 1 elements. V and intersect. Non-trivial. All right, let's pause for a second and do a quick sanity check. Does this give us the right notion for zero-dimensional spaces? So this is saying we can find open refinement such that at most one element can intersect non-trivial. So in other words, we have a disjoint open cover, right? So we have a cover by closed set. So this does make sense in zero-dimensional. And more generally, but we'll talk about the one-dimensional case shortly. Right, so this is what it means to be at most n, and then n, if it's equal to n, if n is the least such integer, such as this holds.
And why do you need X to be compact metrized?
Well, you don't need X to be
Finite here, not locally finite. Locally finite intersections are more complicated.
Absolutely, yeah, absolutely. But I guess it also makes sense for locally compact spaces, but metrizable. There are other notions of dimension which all coincide in this metrizable case. not much other. Right, so equivalently. So this is a very useful way of thinking about it, which will get us to the notion of nuclear dimension. So equivalently, W admits an N decomposable finite U. U, yeah, okay, let's say U is UI, such that I is an I. Right, so what do I mean by N decomposable? What I mean is I can decompose the index set into N+1 pieces. So I is the disjoint union of I0 disjoint union IN, and all of the open sets corresponding. So let's think of these as colors. So let's say in the N=1 case, I have two colors, red and blue. And all the red sets should be pairwise disjoint, and all the blue sets should be pairwise disjoint, but they can't intersect each other. So such that for all K, and then for all I1, I2 in IK, I have U, I1 intersect U, I2. I2 is empty.
So U is a refinement of W, right?
Yeah. Okay, so I have a refinement where I can break it up into N+1 colors, and in each color I have pairwise disjoint sets, but the colors can intersect with each other.
The indexing set I is the same for W as for U.
Not necessarily.
Not necessarily.
It's just that, you know,
Fine.
yeah, it's a refinement. So each UI lives in some element of W,
Okay,
but there could be many more.
okay, so I is a substance.
And the refinement does not need to be finite.
Yes. I want it to be finite. Let's just say finite. All right, so but just think of this in terms of colors. Okay, by the way, the fact that it's equivalent is not quite immediate, but it's true. In one direction it's easy, the other direction requires a little bit of work. This is proved by Fishbeck and Winter in one of their papers. Let's have a picture. So here is the open interval, and let's have some colors. We have red sets. And then we have blue sets. Okay, so nice. One job. Let's make this. Okay. Right, so this is what you should think of.
One more. The beginning.
At the beginning, yes. Yes, right. All right, so this is what we should think of for the refinement U. Right, so imagine we started with some W and we refined it like this. Okay, so we have two colors, each of the colors that pairwise disjoint, but the blues can intersect the reds. All right, so now let's go back to the proof of nuclearity. So let's say in that proof, we assumed that X was finite dimensional. And so suppose in the proof of nuclearity, did I include one that was necessary? I guess this one. Okay, yes, it's true. All right. In the proof,
It's the empty set.
yes, good quite. Right. We assumed that first of all, the dimension of X is N, finite. And this open cover we took, let's assume that it was also N decomposable. And the open cover U is and decomposable.
So then what's the meaning of dimension there, like in this X?
In the sense that
X
I
is
just,
just a compact metric space, like the,
yeah, in the sense that I just defined. In this sense,
okay, this looks like Hausdorff dimension. Does it? No.
this is the Lebesgue covering dimension at the top. The fact that we can find a refinement such that no n+2 elements can intersect in trivial. That's the definition of Lebesgue covering dimension, if you like. And I'm saying it's equivalent to this description in terms of n+1 colors.
Mhm.
So for finite dimension manifolds, the dimension of a manifold coincide with this.
Yes.
Yeah.
Yes, absolutely.
It looks like this Hausdorff dimension. What's
I
What's
don't, I couldn't comment.
okay, sure.
You need spheres, no? Sphere, you need spheres and metric space.
Yeah, it depends on the shape of balls.
Balls.
That's a good point. I mean, this is not, it's a topological notion. I mean, it's not at all geometric.
But that's the beauty of it.
And it has to be dimension does not need to be an integer, it can be.
Yeah, also a good point. Yes, yes.
But
Yeah.
you need not manifolds, but topological manifolds. That's what you have in mind.
Well, it's for any, as he said, compact metriable space.
Yeah, but you said that it coincides with the.
Oh, yes. Yeah, I think so. Yes, of course.
But for a fractal, as we said, they are different.
Yeah, because it will still be by definition an integer.
Yeah, I mean,
I don't think it's out of dimension.
and as Julius points out, very much for fractals, you will get something non-integer. Yeah, typically. All right, okay, so but by dimension, I mean this, and then where I'm using that, I'm saying, remember maybe let's go back to the proof of nuclear. Right. So we picked the finite set and we picked the next one and we chose open cover, and we made sure that the sets are small enough so that each of the functions varies by most epsilon, right? But then we can take a refinement of this to get something even smaller, where this still holds, but also we have this n decomposable property. So we have these n+1 colors, and we within each color I have disjoint open sets. So that's what I'm going to see, and then I'm going to in fact, keep the same map phi and same map psi, but I'm going to show that this Cn can be decomposed in a way corresponding to the colors. That will get us to the definition of nuclear dimension. Okay. Is n decomposable. So let's write I don't know, B to be C to the n. And let's write Bk to be ik copies of C to the k. So for A equals 0. Right, to remember these IKs are the colors. So I have n+1 colors. So in other words, I'm writing B as B0 direct sum, B1 direct sum, Bn. Right, so the colors give me a decomposition of the finite dimensional space C to the n into these n+1 pieces. All right, so as I said, I'm going to keep the same map phi and the same map psi. So I have
Wait, so tell me again, please, what was IK?
right. So in the definition of decomposability, I can decompose the index set into these n colors.
Yes, okay,
So each set ik represents a color.
okay, thank you.
Partition of indices.
Yes, yes. This is an excellent term. Partition of indices. Okay, so let's remember, I'm writing A is C to Cx, and B is B0 Bk. And this is in fact C to the n. All right. So I have A, and I have my identity map. Then I have my map. Okay. Phi going down into B0 direct sum direct sum b to the k. I have my map psi. Okay, this phi, remember, it was just a star homomorphism, in fact, in this commutative case. It was just given by these evaluation maps. So in general, for the definition of nuclear dimension, we want this to be completely positive, as in the CPAP, but also contractive. So certainly for this, if it's a star homomorphism, it's also contractive, all right? In general, we want this to be CPC. And again, we want this diagram to commute up to epsilon on my finite set F. And this sign is going to decompose as a direct sum as well. Yes. So I mean, sine, oh, not k. Sorry. And so sine k is sine restricted to b. All right, so let's now ask ourselves, what can we say about this map psi k? Remember, each so here was also not supposed to be k. And
Алло, Юра, здравствуйте.
Yes, sir.
Можешь, пожалуйста, со мной зайти?
Хорошо, сейчас.
So is there a question or what? Are you asking a question?
I suppose it was in Chinese.
okay, I didn't get it if there was a question.
Okay, let's go on.
Ask again, if you want. Okay.
Right.
All right, all right in the chat. All right, so
Right.
let's ask ourselves, what is the structure of each of these psi cases? So remember, so psi is just given by this map that was sending an n-tuple. Got sent to lambda I, rho I, right? So now if let's pick the color K, right? Then I know that each of the sets in that color are pairwise disjoint. So when I restrict to the indices represented by that color K, I'm mapping to something where the partitions of unity, the elements rho I, live on disjoint sets. So in other words, I'm mapping to orthogonal things. So that's the extra structure I have. That each psi k is what's called order zero. It preserves orthogonality because it's mapping things in different components to orthogonal pieces. So each of these, again, is going to be completely positive contractive and order zero.
I must admit, I'm a bit lost. What are we proving right now?
I'm telling you what the definition of nuclear dimension is.
I'm just telling us.
I'm telling you what the definition is, and I'm motivating it by saying that in the case where X is a finite dimensional topological space, the structure we get is what will motivate
It exemplifies of what you're saying.
exactly.
Order zero classically means disjoint supports these components.
I see. Okay, then the terminology is good then. So it means, just to be clear, that if A, B are in C to the I K and A, B equals zero, then psi K, A, psi K, oops. A, B equals zero. Okay, so again, just to repeat that, what does it mean for A times B to be zero in C to the IK? That means that they live on different components. And when I map with psi k, I'm mapping them to some linear combination of these elements, rho I, but the sets in that color K are disjoint. So if I take things in different components and I map them to disjoint open subsets, then I get something orthogonal in C of X. All right. So each of these is order zero. I mean, between different colors, I may not have this orthogonality, but in each color I do. And this is the definition of nuclear dimension at most n. So in other words,
Do you also ask that A is separable?
no, I mean, yes, if I want to define it as a limit of sets, but no, I think this definition makes sense, even if it is not separable.
But in the case that X is symmetrizable, then have the algebra separable, so.
That's true. That's true. So I guess what I'm showing for you is that the nuclear dimension of C of X is at most the dimension of X. If X is compact factorized. But the definition makes sense even in the non-separable state. Okay, I mean, right, so the definition of nuclear dimension N means that I can, if you give me a finite set F and a finite set epsilon, I can find some finite dimensional C-star algebra B, which decomposes in this way, and a CPC map going down into it, and direct sum of CPC order 0 maps coming out of it, such that this diagram commutes up to epsilon in a finite set. All right. Let me just say something else. In fact, we have even more than this. So it's not just the case that each psi k is contracted, but the whole psi is contracted. This map is contractive if I take all possible indices. So if I allow, that's a stronger statement. I'm not just saying that each of these is contractive, I'm saying the whole direct sum is contractive. That's the definition of decomposition rank. So in fact, psi itself is contractive. Not prestige. Right. So what this shows is that the decomposition rank of C of X is at most mx. This is decomposition rank. All right. I will just say that in fact it's not just
So can I ask a quick question? So
yeah.
So this B is not an algebra. It's just when you factor this.
No, it is a C-star algebra. Yes. I mean, this B is in this commutative case it's C to the n. In general, I want it to be a finite dimensional C-star algebra.
C to
Pointwise. Yes. Functions on endpoints.
functions on C to the n is not an algebra, right? It's I don't.
Yeah, yes, it is.
It is functions on endpoints.
Okay. Pointwise. Okay. Sure.
Okay. Yeah. All right.
So if A is unital, then you can always replace in the definition phi and C to be unital.
Yes, absolutely. That's true. I mean, that takes proof, but yes, it's true. If A is unital, we can require these to be unital, completely positive maps. A, but I mean, we can require this. Not each psi k
Okay, so
has a unital order 0 map would in fact be a star homomorphism.
right.
Right, which may not exist. You may not have any star homomorphisms from matrices into. Right. Okay. So yeah, so actually all of these are equal in the commutative case. So dr C of X is the nuclear dimension C of X mx. I'm not going to show you the other direction. Okay, all right. It's so in this sense, in the nuclear dimension and also the decomposition rank, they are non-commutative notions of dimension. It's not at all obvious that the nuclear dimension, oops, I'm going to show you, is which paired in the statement for the classification theorem is the right notion of non-commutative dimension. In fact, Wilhelm, so this definition is due to Wilhelm Winter and Joachim Zacharias. But Wilhelm wrote a series of papers on different notions of non-commutative dimension. So some precursor notions included the completely positive rank. I think I was great when he came up with. This was succeeded by the homogeneous rank. Then came the decomposition rank. Then came the nuclear dimension. So it took a while to realize what is really the right notion. And why would you want to work with this nuclear dimension and not the decomposition rank? I mean, you might think it's not such a big difference, right? I mean, one is just requiring the whole map to be, the whole site to be constructed as opposed to each individual piece. But in fact, it makes an enormous difference. So the theorem.
What is decomposition rank?
That's what he said. The whole is contracted.
Exactly. The whole site, not just pieces. Yeah, decomposition rank, this means, so let's go back. Nuclear dimension, this definition, each side K was meant to be contracted. If I demand that the whole direct sum is contracted, that's the strong motion decomposition rank N. It might seem okay, it's a little stronger, but it can't be that much. No, but it's dramatically stronger because if A is separable and has finite decomposition rank, then it has to be quasi-diagonal. I'll briefly tell you what that means. But in particular, quasi-diagonal C-square algebras are stably finite. Okay, so
You are defining dimension of X or nuclear dimension of X. You mean the minimum
Yes.
number that
absolutely, yes. I never wrote this down, but yes, when I said what it means to be less than equal to n, to be equal to n is the minimum. And all right. So in the classifiable category E, there was this dichotomy that could be purely infinite or stably finite. And I'll make this clearer in time. But all of the purely infinite ones have infinite decomposition rank. So that's why that the nuclear dimension might be a sort of a more all-encompassing notion of non-commutative dimension. Let me briefly say what quasi-diagonal means. Quasi-diagonal means that I can embed A into this.
So the composition rank is always less or equal to the nuclear dimension, right?
The nuclear dimension is less than or equal to the decomposition.
Vice versa, the opposite.
Vice versa.
Yeah, because having finite decomposition rank is a stronger notion than having finite nuclear dimension. So finiteness of decomposition rank should imply finiteness of nuclear dimension. So that means it should be bigger.
Okay.
By the way, I guess I didn't say that if there is no such n, if you can never find decompositions, it's infinite. All right, so quasi-diagonal means that I can find such embedding. Let's say quasi-diagonal plus nuclear means this. Yes, I can embed A into this. Okay, so as I said, purely infinite. Objects in this category E have decomposition rank equal to infinity. But the purely infinite algebras, this is by Kirchberg, they are O-infinity stable. O-infinity we saw already in Gillis's talk. It's this universal C-star algebra, and O-infinity stable means that A tensor O-infinity is isomorphic to A. Hence, I mean, this is very non-trivial. This is by Kirchberg's deep work. Hence, they are also Z-stable.
I didn't have to say which tensor product because O-infinity is nuclear.
Yeah, good point. Yes, hence they are Z-stable. So Z-stable just means the corresponding thing with the Jiangsu algebra. So A tensor Z, okay. A tensor Z is A tensor O-infinity tensor Z, because I'm assuming it's O-infinity stable, but O-infinity is itself Z-stable. This is A tensor O-infinity, which is A. By the way, so both O-infinity and Z have the same K theory. We have K0 group is the integers and K1 group is 0.
O-infinity has more traces, has traces.
O-infinity has no traces, purely infinite. No traces at all.
like Z. Sorry, there is one space on Z.
One trace of Z. Yeah. So the Z is the stably finite analog of O infinity. Because the thing that distinguishes it is that it has this trace. But they both have the same K theory. So the K theory, which is the same as the K theory of the complex numbers, by the Coulomb theorem for tensor products, which I will mention maybe next time, the K theory of A tends to infinity is the same as the K theory of A, the same as Z. That's why O infinity stability and Z stability are very important in the classification theorem, because tensoring with them doesn't do anything to K theory. So the classification theorem, then, the Ellis invariant cannot distinguish between A and A tends to Z in the finite case, or A and A tends to infinity in the infinite case. So these are sort of necessary conditions for algebras to be classifiable. Okay, so the purely infinite objects are O infinity unstable, so they're Z stable, hence have finite nuclear dimension. Okay, this is a very, very non-obvious fact that I'm telling you, that Z stability, this absorption A tends to Z isomorphic to A, implies finite nuclear dimension. Let me state the theorem. Theorem to various subsets of these five authors. So Castells, Evington, Bhishan. So if A is a simple separable nuclear, then being Z stable is the same as having finite nuclear dimension. So the dimension of A is less than infinity, if and only if A is isomorphic to A tends to Z. Wait, this is a very, very deep result, but the upshot of it is that in the statement of the description of the classifiable category, I could have replaced finite nuclear dimension with nuclear plus Z stable. Okay, maybe just to finish, I will just say, so in fact, so every simple, okay, not every A and B has a nuclear dimension equal to 0 or 1. There are just two
That's amazing.
possible values.
That's amazing.
And in fact, 0, if and only if the algebra is an AF algebra. Yeah. So, you know, a limit of finite dimensional algebras. So in particular, the Jiangsu algebra itself has nuclear dimension 1. All right. Okay, maybe in the last minute or so, I will say that so as I said, these are just 0 or 1 as the possible values, but there are known simple C-star algebras which have infinite nuclear dimension. So these are some C-star algebras constructed by Jesper Willitsen. So Willitsen's sort of exotic examples are simple. In fact, I think AH algebras. What is AH? Approximately homogeneous. So sub-homogeneous, remember, meant it was a sub-algebra of continuous functions into matrices. If I dispense with the sub-algebra part, that's homogeneous. Okay. So it's just a limit of continuous functions on from some space into matrices. perhaps with dimension. I mean, he doesn't, his examples preceded the notion of nuclear dimension, but his exotic behavior was what's called perforation in the K0 group. And Z-stable Caesar algebras cannot have perforation. So these cannot be Z-stable, so they cannot have
And this comes from Kenneth.
This comes from, I suppose, yeah, exactly. All right, and then these first examples led to the counterexamples to the preliminary Elliott conjecture by Andrew Thompson. So I'll stop there for today.
Okay, thank you so much. Yes, please. Wow. Up to a single second. Any questions, comments?
I have a question.
Yeah.
What are simple examples? They are of nuclear dimension greater than 1 outside this
Commutative range.
Yeah. So if I take just an n-dimensional space, then the nuclear dimension of C of X is
What is commutative?
committee.
Yeah.
What about limits?
So I think you need something non-simple, because I think this you need something non-simple, because this fact about only attaining these two values, I think it holds quite generally. So any simple Caesar algebra, I think maybe simple separable something. Yeah, you're going to get 0 or 1. I mean, of course, if you take something non-nuclear, you'll get something infinite, but finite, non-infinite, you need something non-simple.
Yeah, you want to ask it.
Yeah, so so is there some philosophy to produce like a simple C-star algebras, like
To produce simple in the sense of no non-trivial ideals?
Yeah. I mean the simple in this category E in your sense, like simple like that.
Yeah, so for example, if you're building one of these inductive limits, you want these eigenvalue maps that appear in the maps phi n to have this delta density property. So they should kind of fill up the whole space eventually.
Okay.
You want to be enlarging supports. You want the support of any function to be spread out eventually. But I mean, of course, in things like cross product examples, you want some kind of freeness of the action to produce, because you want nothing to be fixed. You want fixed orbits.
Could you explain why you don't have simple examples of nuclear dimension greater?
No, I can't. I really can't. I mean, I think this is very surprising. Very, very surprising and mysterious to me. Maybe not to these authors, but to me, yes. You would not expect this. And then it does make you wonder, well, are we?
So this means that the higher dimension must produce some ideas.
I think so, yes. It doesn't, it makes you wonder whether there might be some other notion of non-commutative dimension that does allow for more variety of values in the simple setting. I don't know.
But is a theorem
that you want to get 0, 1?
No. That among simple.
Yes. Yes. So I sent you every A and E, but I think it was more generally than what I wrote. I really think it could be just something simple, maybe with a few extra hypotheses. I'll check and I'll get back.
Let me wind it up by making one quick comment and asking one simple question. So a quick comment is as follows. I fully subscribe to the idea that the fact is not an idea, that when you go non-commutative, certain concepts that are classically all the same, they just diverge. We're studying with Mariusz Topolsky and other Jacelon and Eusebio Gardella, we're studying local triviality dimensions. So for commutative, have compact Hausdorff topological group acting on compact Hausdorff topological space, all these coincide. But then you go non-commutative and we had to introduce 3 different types of these dimensions of these actions. Right. And indeed, in some very simple examples, like matrices, simple graphs, algebras, and actions of Z2, not very complicated groups, you could see that this concept diverge. So that's, I can easily believe that what you are saying, the composition, blah, 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 is the same thing, you go somewhere else, it's totally different. Yeah. So we observed the same effect in our dimension studies. but these are studies terms of actions on C-star algebra, not of C-stars themselves. Okay, now my question is, I'm sorry, I just cannot resist it. The reason why you are not telling us a proof of the classification theorem is because you don't have time, not because it itself is classified.
Let's see. I think, yeah, the real reason is that
Classified information.
Sorry, couldn't resist.
yes, this is, but totally would like it. But the real reason is that I'm not qualified to do this. My specialty is really the applications and use of this term rather than the term itself.
Okay, let me stop recording. Thanks again. Stop.
So now classified questions more.